In this recording, I want to explain how to do the Quest Unit 4, number 13 and 14 in the homework for this unit. First of all, when we look at the drawing, we want to translate what they've given to us into a free body diagram. So as you can see, we take a look at the angle that's provided, in this case is 44 degrees, and there are two cables supporting a vertical weight. The downwards force is going to be 63 newtons. So we can label our free body diagram with the blue arrow here is representing that downward force of 63 newtons. The T1 is representing the tension in this cable that's connected horizontally. The T2 is representing the cable that is at an angle. We're going to want to think of this as having vertical and horizontal forces. If we look carefully at our free body diagram, the downward force is 63 newtons. We know the total force in the vertical direction, both downwards and upwards added together, must balance out to zero. The object is not accelerating, therefore the net forces are zero. So if I look at this hypotenuse and think about it in terms of the components, there will be a vertical component, that's the green arrow here, and there'll be a horizontal component, that's the red arrow. The vertical component has to equal 63 newtons for that force in the vertical direction to balance out and have equilibrium. So I know that whatever this force is, this also has to equal 63 newtons in this situation. I can use that as part of the triangle then to figure out what the hypotenuse is, and that's what letter A is asking about. It says, what is the tension in the cable slanted at an angle of 44 degrees? So I'm going to redraw that down below here, and I'm just going to take a look at what this might look like. So I'm redrawing this triangle and just looking at this part of the free body diagram. So here I have the 63 newtons upward. We're going to solve for this hypotenuse, and I know this is my angle of 44 degrees. Going back to what we know about SOHCAHTOA, I think the best option here, because I have the side opposite the angle, is to use sine. So now I'm substituting in what I know. The side opposite is 63 newtons. The angle is 44 degrees, so the sine of 44 is 63 over hypotenuse. Solving for my hypotenuse, I can then plug in those values, and I end up with about 90.69 newtons. That would be the amount of tension or the amount of force in this hypotenuse. 90.69 newtons for that side right there. Okay, the second part of this problem is asking about the force or the tension horizontal. Again, when we go back to our free body diagram, the horizontal force is represented by this T1, this black arrow. Because it is in equilibrium, the sum of forces on the horizontal have to add up to zero. So therefore, I know that the T1 is equal to whatever this red arrow is in that horizontal direction. So I can then find that with my triangle once again. I'm just going to redraw it so I have a idea of what to do. I'm using my vertical force of 63 newtons as one of the sides of that triangle. I'm going to now solve for the adjacent side. I could use the cosine, but I'm going to use, because I know the hypotenuse now, but I'm going to solve it with just the tangent. I end up with about 65.24 newtons of force in that horizontal direction. Okay, coming back up to what we know, so I'm going to remember that 65.24 newtons. Remember, because it's in the horizontal cable, in order to have the net force be zero, the force net in that horizontal direction has to be zero because it's not accelerating. The sum of the forces in the horizontal would be tension 1 of T1 plus the force here, let's call this T, let's call it horizontal, plus TH has to add up to 0. All right. In other words, these two are the same side. So if I know what this is, I know what this is. In this case, it is at 65.24 newtons. So that's my answer. 65.24 newtons. Hopefully this helps explain a few of these problems with tension. Always go back to the free body diagram and think about what forces need to add up so that the net force in these cases is 0. Thanks.